I'm Mark Sanchez Artigas, the coordinator of the CloudSkin project. So today I will give just a brief overview of the project, because as the other project, there is many technical details that cannot be nailed down to a simple 10 minutes presentation. But okay, I hope that you get the idea of the project. In the consortium, we have like around 12 participants. They came from different countries. We have people from UK, Imperial College London, IBM from Switzerland, Barcelona Supercomputing Center. All of these partners has been selected based on a specific expertise. So in the end, we can craft a very good CloudSkin platform. So I don't want to spend a lot of time on that, but our approach is essentially looking at the whole Continuum environment. As you know, this spans from the centralized cloud, that it has like, let's say, superpowers, but at the same time, it means that you have to be locking in APIs and things like that. Then we have another layer that's called the edge infrastructure layer that allows not just communication between the edge to the cloud, but as well, we can manage to get communication between the edge to the edge servers and clusters, so we can get a lot of powerful benefits of that. And then in the last layer, we have IoT devices that perform real-time data processing. So as much closer we get to the IoT devices, we can get, in principle, higher speed ups. And as long as we go to the cloud, we have more CPU or computational power, but at the same time, we are adding extra latency that can be critical depending on the use case. So in our project, we have essentially three main challenges. The first one is that managing the continuum. Here you have an example of a pipeline that occurs in one of our use cases. We have cameras that are producing a lot of video frames per second, assume 32, 64 frames per second, and they have to go to a phase for processing that image, pre-processing that image, and then detect objects. That information that comes from adding the metadata plus the images that has been transformed finally have to go to an object recognition phase using, for instance, TensorFlow to detect that, okay, that's it's not just a simple object, but in the end, this is a vehicle. And this should be done with stringent SLOs. That means that, okay, the end-to-end latency of that processing could be less than second. This is very important. So here we have many issues because we have to, in the end, determine smartly where to place the task. So we have like requirements specified by the users, and then we have to decide, okay, this task should be run as a container in that place, or should be run as another virtualization technique in another place, and we have to have n replicas of the same task of the pipeline to speed up the whole computation. So this is a very complex task that requires considering network efficiency, but as well, as we see in the following slides, as well data privacy and other kinds of elements that are becoming part of the continuum. The other aspect that we are working a lot, this is similar to what the people from EdgeLabs presented this morning, is about virtualization. The thing is that if we use simple VMs or containers, they are very well for hosting long-running applications, but the downside of these technologies is that typically they are slow to start and have high memory demands. So this is very bad in terms that if we have to move computations to weak devices, maybe the huge memory footprint makes that computations unfeasible in that devices. So this is something that must be corrected. And even if you prepare a container, depending on the architecture, could be incompatible with another architecture. So one of the main limitations is that the containers, okay, can be used for running certain kind of computations, but it's not enough for managing the whole continuum. So in our case, we are also using WebAssembly, because in the end, WebAssembly is very interesting. It's virtualization is not at the operating system level. It's more related to language virtualization. Could be seen to a relationship with Java. Let's say by code that you run, you create a Java application. This is compiled to a bytecode, and then it's run as within a virtual machine. But in that case, it's not just for a single language. It's polyglot. It means that you can take C, C++, Rust, Go, and other languages, and this can be compiled to this WebAssembly binary format that is very small in size, it's lightweight, and the virtual machine's execution model that is stack-based is very fast to spin up. So in the end, we can get that the same device, for instance, a Raspberry Pi, it can include 10 times more tasks that could be done using simple containers. So in the end, we are managing in the project containers, but mostly we are interested in running things using WebAssembly, essentially. And in the also continuing with this challenge is that we are considering that security must be in place in the whole project, because in the end, if we are targeting the Continuum, maybe we have to migrate computations from one edge server to another server, and maybe this server cannot be trusted. So we have to provide the means to ensure that this computation in the end it can be considered trustworthy. So we know that it's been run as it should be. So what we are doing here is running WebAssembly inside the TEs. So we can protect the confidentiality data. This is combining the WebAssembly with Intel SHX and SCON that is also appearing in the Edgeless project technology. So in the end, we can provide the same idea of confidential containers, but in that case, WebAssembly modules that are as well confidential. So combining this, we have a virtualization technology that can be moved around the continuum, plus some security protections to ensure that computations are really secure. And finally, there is also something that is again related to edgeless. So in the end, it seems that we are targeting similar topics, is that if we think about that many tasks could be not just microservices that run forever, but are computations that are ephemeral, that let's say they last for 100 milliseconds up to 3 seconds. And they are provided in large parts. So imagine that we are receiving thousands of images and we have to classify them in a few seconds. This is a large part. We have to keep the means to store the state of that classifications or the state of that information. So here is that the serverless model, as appeared this morning in the Edgeless, is that essentially is stale. It doesn't have any kind of a state. So here in the project, we have been providing means and technologies that allow us to combine, let's say, the serverless model with stale functions, but adding this stateful layer to guarantee that we can move computations, but as well we can move the state across the whole continuum. We target batch applications as well as stream applications. So combining these three challenges, we have partners working in all of the challenges. Our final idea or our final mission is design a cognitive cloud continuum platform that can exploit all the available cloud edge resources that are in the continuum. This could include from a Raspberry Pi up to a high-end server in the cloud, and this should be using similar technologies. So in our platform, we divide it in 3 layers corresponding to the same challenges. And it fulfills several functional requirements, but the important thing is that we have an orchestration layer that includes a learning plane. The learning plane is collecting telemetry information, and then it's running several ML and AI models to decide where to place the task, and even if the task should migrate between the edge and the cloud, or between the edge to the edge, etc. When this is decided based on telemetry, this is like a kind of loop, a feedback loop that is all the time running. This is that decision is communicated to the control plane. That could be a Kubernetes or another kind of orchestrator. In the project, we have, for instance, nearby computing that provides its own orchestration. That orchestrator takes our decision and then does the best to migrate or decide where to put or move a given task to a specific place. So in our case, in the platform, we consider 2 scenarios. The static one, that we have the requirements, and from the requirements, we can decide at the beginning where to place the task. But as well, we have a scenario that we are running, things are changing, the conditions are changing, so we have to exfiltrate computations to the cloud, or we have to move a given heavyweight task to the cloud, or etc. And this is related to virtualization layer that we combine, as we said, confidential execution of containers and WebAssembly modules, using as well serverless functions from the cloud, using lithops, that is the technology we're providing from our university, in case you are B. And this all together is combined and the state exchange using the infrastructure layer that essentially manages efficiently streams of data. We have a camera, it's like a series of video frames that go through a video analytics application. So we need to manage that state, keep it consistent, keep it well loaded in case that something fails. And as well, we use a multi-tiering service to move data around. So essentially, this is the idea of the platform. All the code similar to the other project, I presume it's again open source. Even IBM is and the private companies is open sourcing everything to the platform, and these are available in the corresponding GitHubs. In our case, in the project, we have 4 use cases in different domains. So we have one, it's about vehicle mobility. You need to think about a circuit that is equipped with cameras and small servers. And we have vehicles that are running across the circuit. And the idea is to perform video analytic tasks across that circuit. So the thing is that because the servers are expensive to use, the idea is to move the video analytics application following the car. If the car is moving, advancing in the circuit, we move the state as well. We move the task to the next server so we can follow the car, giving room for another application to run in that server. We have another scenario that is the one we are managing from URB, our university, that is the metabolite annotation pipeline. This idea is that we have collaborating with EMBL, that is European Molecular Biology Laboratory. The idea is they have a complex pipeline that in the end tries to classify metabolites present in biological samples. And there is a final stage that is related to classify some of that metabolites. So this project is very active. It has thousands of data sets. And there is a lot of researchers that every day are submitting new data sets with a bunch of images. The interesting aspect of that use case is that data say we don't have a fixed number of submissions. I mean, in a given day, you can get a lot of data sets with a variable number of images, but the next day, you can get just a small number of submissions and with a small number of images. So the workload is very variable, and this makes it very challenging because we have to adapt all the time to the specifics of that use case. We have another one that is for computer-assisted surgery. This is based on Dresden in Germany. There is an hospital that is like getting a video from the surgical intervention in real time, and this video goes through a video processing stage to assist the surgeon and make a better surgery. This is, again, a very stringent use case because you have to provide real-time latency and provide good images with good quality with all the data tag within the images to assist the surgeon. And finally, we have, again, an agricultural data space that is managing some pipelines to, for instance, to detect problems with water and etc. that combine geospatial information and with CPU and task writing in MPI. This is essentially more or less our 4 use cases. Here you can see that most of them are tended to be edgy, I mean going to the edge, and there is a part of them that are using a little bit the cloud. So to conclude my talk, is just an example of one of our use cases. This one is about metabolomics. So here we have developed a specific software based on lithops we call it LithObserve, and the idea is to combine resources from the edge and the cloud in a single system that is able to process, let's say, between 100 to thousands of images using a trained ResNet 50 model with metabolites. And here the main challenge is, okay, we have like a variable pattern that we don't know if tomorrow would be like 10,000 images that will touch the system. So how to anticipate that, how to provide mechanisms to optimize the right number of resources. So we're working with that, providing models that predict the cost and try to anticipate the dataset arrivals that are touching the system. And these are combining Cloud Functions with Docker containers to be run in the edge, with as well WebAssembly containers using a standard that is called WASI-NN. That is very useful because you can run WebAssembly containers together with GPUs. And as we can see here in the platform, we have the learning plane. The learning plane is the one that is responsible for providing the resource provisioning decisions. This is from information that is retrieved from the orchestrator because it's the one that is providing telemetry information about how many datasets are being queued to be processed. Then there is the lead up system that is providing when the decision of you need to use, for instance, 100 serverless functions, then leadups goes there and launches that 100 functions and keeps them alive in case that one can be reused. And there is a system that controls that using a master-slave architecture that is like giving batches to the corresponding executors to make the classification. So essentially in our system, we're running 16 to 12 to 32 images batches that are a good number for providing a good throughput. So this is it. We implemented our solution. Now it's been in the process of being implemented in production at Embel. We compare it with the old solution that was called Metaspace. And by the moment, because we are still in the second year of the project, we got a throughput that is between 10 times to 150 better throughput with a similar cost using Cloud Functions. So that even the performance per dollar could be between 5 to 10 times. And now there is an interesting challenge because performing confidential image classification with this is not simple because these are at a lot of overhead. We can be like 50 times slower if you put the whole model there to be run within the T. So we are analyzing ways to, take several layers or certain layers of the model and just push it to the T and leave some other layers completely public. So here we have to protect a little bit the confidentiality of the data, not the confidentiality of the model itself. But here there are a lot of attacks that can be done against the model. So we are working with that with the people from SCON to see the best way to achieve that. So this is just a quick summary of the project. If you have any question or something, we can write me to marksanchez.urbcat and we'll be very pleased to respond to your questions. So thank you.